Hi everyone. Can you guys confirm that you can hear me?
Yes.
I can hear you.
Okay, that's good. Thank you. Cool. So the first part we're going to the theory, but I already put the GitHub link on the chat. So if you want to download that, you can get started on that. There's a task poll there, I think. So if you guys want to check if the poll is working before, that would be cool too. And hello everyone who joined again. I'm Isabella. I'm giving this tutorial. Okay, we'll wait a little bit more. You are 22. I think you're supposed to be 35. Okay, let's wait more 2 minutes and then we start. Oh, there's somebody at night. How brave. How night's it 7 or like 8? Oh, good night. Good evening for you then. I'm pretty much tired. Okay. Okay. Okay, so to recap, there's the introduction to dimension reduction in R. I'm Isabella. The link for the tutorial for the markdowns are on the chat. And we are just gonna wait 2 more minutes to see if anybody shows up late. Because you're supposed to be 35 and you're 23, so maybe a few faces will join us a bit late, but I'll go ahead and I'll share my screen. So can you see my screen? I can see my own screen. Can you see my screen?
Yes.
Okay, cool. I like the participation. Let's add another poll. You're gonna need that. Okay. Cool. Okay. So does anybody have any questions right away? Or is everybody good? Do you feel like we can start? If anybody joined later, everybody's gonna join a little bit later. Okay. So good morning and good afternoon. To me, it's good afternoon. So you can see my screen. So can somebody say yes if you can see my screen in full screen now?
Yes.
Okay, good.
Yeah.
Okay, so this is Introduction to Dimension Reduction in R. I put all the materials there, the slides are there, and they're also on the platform if you need them. We have 4 different markdowns, and so today we're going to learn some tidy models, we're going to use Vegan and Mass, we're going to do some Python from R using Reticulate, and we're going to do some UMAP. And the section it's a bit longer and divided in 4 sections, so we can go through it in a reasonable pace. So don't be scared because it's a 3.5-hour tutorial. So I am Isabella. Thank you so much for choosing my tutorial. It's very nice that we share some interest. And I'm hoping that today we can achieve your learning goals today. And if you have any questions, you can contact me in any of those platforms. I'll actually leave my email in the chat. I think they're recording the session to post it online, so it's not here because it's going to be spam. But don't hesitate to contact me if after the tutorial you have any questions. So some guidelines for today. This is designed so you can learn basically a bit on the go with help from me. And I need the feedback in general because otherwise I'm talking to a screen. And the idea to have the tutorial is, I guess, a little bit of interaction too, because otherwise you could just watch a video online in dimension reduction. So please give me feedback if you cannot hear me clearly, or if I'm speaking too quietly, if I'm speaking too quickly. You are invited to ask questions anytime. So the way I have it here right now, I cannot see the chat, but I'll be checking it from time to time. But please don't hesitate to turn your mic on and talk to me. So just seeing chat right now. Okay. Also, the tutorial, of course, is in English. But if any of these languages you're comfortable with, and sometimes between very specific high-level topics, it's hard to translate between one and another. So if you have a very specific question in one of them, I'll try my best to answer them. So today our goal is to see how we can use R to do dimension reduction. And it's not going to be a super in-depth course of dimension reduction. We're going to discuss some of the methods we're going to use. And this is also not an exhaustive list of reduction methods. There are too many. And there are links to the tutorial and the sources all throughout the slides. But if I make mistakes, they are my own. And if you notice one, please tell me so I can correct them. So the tutorial is planned so we can go through it in a reasonable pace. So we have spare time. If you don't understand something, please ask. The goal is really so we can have this like shared experience. So the way the tutorial is based, those 3 books, they use some terminology and certain examples. So if after this tutorial it was not enough for you and you want to integrate with any of those books, I kind of designed it in a way that you could do that rather easily. So check those if you want to learn more. So we're going to start section 1. And does anybody already has any question? Anybody does something? No? Everybody's good? Just going to make a poll. And you're going to say, is this good for now? Like, can you hear me? Can you see my screen? We can try to have some interaction here. No questions for now. Thank you, Jeremy. Oh, good. Okay, good. So I'm just gonna launch the poll. And then I guess the other people can join too if needed. Okay, let's go. So, section 1, we're basically going to discuss what is dimension reduction and why we are interested in it. So, I really like this part that talks about how it's hard to work with data, like with modern data, because you don't really know which are your predictors or which are your columns. that are related to your response. So you really need to spend a lot of time studying them and try to understand if it's just a simple or complex combination is going to be relevant. And this is really challenging to do. So dimension reduction is one way to answer that. So we can define dimension reduction as a transformation. And this transformation is one that takes M and makes it smaller than P, where M is the number or the transformed new predictors, and P is your original predictor. So if you had original data same, you just have N, which is the rows, your number of observations, and P, which is the number of your columns, so your predictors. So we're interested in reducing them. And please notice that in this framework, we actually don't discuss how many predictors or how many M's there are in the, I mean, we do discuss that there has a relation that M is smaller than P, but we don't really have a number. We don't need P to be a big data case, which I think sometimes people get a little bit confusing. So usually if we do a transformations and M is equal to P, we say that the predictors are independent and there is no reduction on it. And if P, so if your number of predictors is much, much greater than your N, you have a high dimensional case. So a high dimensional case is usually when you have few observations, but out of the observations you have a lot of data. So that's what it's called, basically high dimension. And dimension reduction does not require your data set to be high dimensional. That's not a prerequisite. So I think that's the two things that are more important. You don't have a limit on, they have a minimum number, because if they are independent, your transformation is going to give you the same result, or it should give you the same result. And that you don't need to have a high dimensional data set to try to perform a dimension reduction. So what are a few of the reasons we would like to do that? First, we would like to represent those predictors. So we would like to have a graph that we could look at and make sense of that. With 2D beings, it's very hard to try to understand a data frame or a table with 30 different columns in it. Our brain just don't process data that way. And also, if you're working with predictive modeling, so if you are doing some machine learning or some statistical learning, there are a lot of models that are sensitive to irrelevant predictors, and especially neural networks for vector machines. And then if you just keep adding predictors, you're not really going to increase your performance that much. And some models, for instance, linear logistic regression, they're very sensitive to correlated predictors. So you are assuming in the model that they are not correlated. So if you want to use a model like that, then you have to transform your data. And that goes hand in hand with this called the curse of dimensionality, which is the idea that as the dimensions increase, the space, like this conceptual space that's formed by your dimensions, increases too fast. It increases so fast that it doesn't really matter how much data points that you have. It's just too sparse to make to have information about it. So you end up not really being able to distinguish what is noise from what is signal, and it causes this very specific curve that's like the peaking phenomenon. As you keep adding dimensions, your classifier or whatever model it is that you're trying to do, it increases performance super quickly. And then at some point it peaks, and then any more dimensions that you add, you actually decreasing your performance. So this is kind of known, and it's a little bit counterintuitive, but also it's one of the big motivations to do dimension reduction if you want working with modeling in that case. It also, it just makes sense that you would not want to have such a complicated model, and you want to keep the minimum number of predictors to have good results, to have whatever acceptable means in your case. And also it might reduce just the cost of acquiring data. If the process of acquiring data is very expensive, then you want to waste resources on that. And also, depending on the case, it might be easy to storage transform data as opposite to the original data with all the features that you have. Let me just check if you guys have any questions. No, so far. Okay, cool. Okay, so we can start looking at the transformations themselves. So one type of transformation is just feature selection. You can just try to filter out whatever it is that it's not relevant for you. In practice, that's really hard to do. It's really hard to do feature selection, especially because you don't really know a priori, unless you have a specific knowledge about that problem you're working at hand, what it is informative and what is not. And it's not guaranteed that you can find the optimal set of features that will explain your model. So you really have to be careful with this approach, and you have to validate it quite extensively. But in general, I think people don't associate dimension reduction with feature selection right away. They usually associate it with feature extraction, which takes your feature and apply a transformation that reduces it. And that's pretty much, it's a really close definition to the definition we just gave before. And if you're interested in finding a list of it, I really recommend the Wikipedia page. They have a lot of information, and it's organized in a way that's easy to see how many types of different dimension reduction techniques there are out there. So the first we're going to talk about, I think, is the most classical one, which is the PCA, which looks like this. So you have kind of this oval shaped with one component going like this, another like this, and each of those components are orthogonal to each other, and they explain the greatest variance in the data that you have. So what it does, it takes your original set and it performs a change of basis such that the average distance between the points are small, but the point itself, the big component that you see, so that factor, accounts for most of the variance that you have in your data. And if you're more at easy with math, this in general is very, like, just to get the feeling of it, it's not very math heavy, but it's the same of doing the eigenvalues for the covariance matrix. So it's very, very straightforward for that. And for classification of PCA, it's very interesting because if you can already plot a PCA and see some separation, we can sort of safely assume that we can build a classifier, or better, a linear classifier for the data. But the opposite is not exactly true. So if you don't manage to see in a PCA, that does not exactly means that you won't be able to fit a linear classifier. So the really takeaway is that it's always going to be an Euclidean distance. So these projections are orthogonal and uncorrelated, so very good for models that are sensitive to this. We just discussed the linear regression, so if you want to fit a linear regression and you might have correlated components, this is a thing you can do. You can do a PCA, and on top of that PCA, do a linear regression. And it has a unique analytical solution, meaning mathematically you usually can solve it. And it assumes that these components that you are creating to reduce the dimensions, that the interactions between them are linear. So that's an assumption you make, and that's going to be your result. So depending on the problem that you have at hand, you have to remember that. That being said, there are some extensions of PCA. So for instance, kernel PCA, it basically takes your data and plots it in a new kernel. So the kernel is this like weirdly shaped, I don't even know how to describe it, it's like a Pringle to me. And then in that space, in that new space you projected, then you can do PCA that, because those data points, they are linearly separable. So that's another thing that it's very interesting that you can do. So even though PCA is very classical, those tiny expansions, they give a lot of flexibility to the method, and it's a quite clever trick. Please, if you need something not clear, please don't forget to ask me. So really tied to that is independent component analysis. So independent component analysis, what it really does, it separates the signal into multiple additive components, and it assumes that those components, they are independent from each other, and that they are basically, there's at least one of them is non-Gaussian, and that they're statistically independent. So it's very easy to understand through the cocktail party problem. So this problem is that you are at a party, and it's a very noisy party. People are talking, there's music everywhere, and you are that person, and somebody sends you an audio file, and you yourself are trying to figure out who's talking in the audio file. So you have two independent sources of noise, which is the two people talking, and you just have a record of it. So we as humans, we can go and identify that rather easily, but if you want a machine to identify it, that's a bit more complicated. So the idea is that those two different sources, they mix to each other, they add to each other. And then you can apply ICA to basically separate, because ideally they came from two different distributions themselves. So it's kind of like finding, it's exactly like finding a latent component in which the latent components themselves become your independent components. If you're familiar with that, if not, just ignore what I say and focus that just the components, they separate those two different independent sources. So just to compare the two of them, because the name is quite similar, ICA, they do that additively, so they're separating components that one by one. And PCA does that by successively doing that. So it first computes the first component, and then the second, and so forth and so forth. And so ICA actually separates the information that you might have, and PCA compresses it. So they are very different in that sense. And PCA maximizes the variance, and ICA actually maximizes the independence or the non-Gaussianity. And ICA has no, it's not obliged to give you anything orthogonal, while PCA will always do so. So it's good to take away the difference between those two. And then we have multidimensional scaling. So multidimensional scaling, it's very similar to those two, in the sense that you also are working with matrix and you're trying to calculate some distance between them. But you really, what it does really well is try to preserve the pairwise distance between the points that you have. And you can basically pass any sort of distance that you can. Basically, if you can calculate distance, you most likely can use MTS. And that's pretty cool, especially if you have a very data that's filled with zeros. There's some specific distance that was assigned to do that, and that's something that PCA will not do very well. It can actually account for several different losses functions when these problems are being resolved, which makes the method quite flexible. It handles missing data. It can handle asymmetrical distances. But unfortunately, because it's so flexible, it's very costly because the solutions are analytical and you usually have to iterate over them. So it is at least N2. So if you have already a data set that's very large, you're probably not going to be able to do MTS on it, or at least not going to be very, it's not going to be very good. It's going to be computationally expensive. And another source of problem from this is because since it has both a metric and non-metric, they kind of go by different names. So metric, people usually refer to it as principal coordinate analysis, or if it's metric, sometimes people that call it classical MDS too. And principal coordinate analysis themselves are different names, had different names, but they all fit into this big category. So you have to kind of keep an eye out. Because you might be just dealing with the same name, the same method with a different name. And it gives you a very similar result to PCA. You have two or more coordinates and you have a projection between them. And in this case, you just, the points in the point, this graph is color-coded for voting patterns. So you can see how each of those coordinates help explain that basically. So just to get an idea how the metric and non-metric work, the non-metric, you're basically just calculating this difference. So the residual sum of the squares, the difference between your new projection and the distance. And it's very parametric in nature. And if you actually use the Euclidean distance, the solution is exactly the same one from PCA if you're using the metric. And it does so first by assigning the points in this near space, then calculating the distance and the similarity matrix, and then trying to minimize the stress function so that the points are closer together. And we will adjust as necessary. I think I may have a question. Did anybody say anything? I had a pop. No? Are we good? Okay. Are you guys still here? Is it too fast? Okay. Okay, I think it was nothing. So, okay, so then it adjusts the coordinate that's needed in order to minimize the stress function. And if it's non-metric, it does the same procedure, but because the function it minimizes differently, it calculates this extra term on top, this function of x. And function of s is going to be isotonic regression. Isotonic regression are those types of regression. So you have an axis, instead of having a line like this, it goes like this, trying to fit the data. It goes like two little plateaus. And so it has to first try to find this function, and then they're going to try to match that to the scale proximity, so like the distance between them, the original distance between them. So this procedure is quite expensive computational wise, so it's a bit slow. It's a bit unfortunate because it's usually good. And it's very common in ecology. Even the packages that we are going to use today to do multidimensional scaling, they're usually designed and created for ecologists. There is this paper that are trying to understand the relationship between how many seeds there are in the soil and the vegetation in South Korea. And this is exactly what they did. They did a multidimensional scaling. So you have one component here, which it's mostly by these different types of soil seeds, and another one here, and then you can see how you can separate kind of like the young forest from this another one that I don't know what it is, and the mature forest in black. It's very used in especially in ecology. I think it's mostly what I use it for. And then we have t-SNE. So t-SNE, it does dimensional reduction a bit differently. It basically calculates this probability that the objects are closer to each other, and then it calculates a t-student distribution, and then it tries to maximize the difference between those two. But what's pretty cool about it is that it is non-linear, and although it originally calculates the Euclidean distance, this can be changed if needed. And the big pitfall is that it does not really preserve the structure really well. And quite related to that is the UMAP. So UMAP, it's based on geometry, and it's based on the specific types of manifolds. So you project this data on these manifolds, and because you know how this manifold behaves, you can basically calculate try to minimize and preserve the relationship between these points on this new manifold they projected into. And contrary to t-SNE, it preserves global structure really well, and it's less computationally expensive, which is pretty cool. And they are pretty comparable. So you have on the right and the left two different data sets. You have the original data, the t-SNE and the UMAP. And you can see that both of them originally, how spread out the clusters are, they're not really reflected on the data. So it doesn't preserve global density, and there are specific versions of these algorithms if you need a problem that requires that. So this cluster here is really big and spread out, and on the original points, you can see that this is not the case. And the same here, like this purplish points, they're really spread out, and they're not really that spread out as compared to this yellow point that's supposed to be really small, and here it's not. And the UMAP does, I told you that it preserves global structure a little bit better, and you cannot really see here, but you can really see on this point. So you have the kind of the view of the world here. And if you project that using other methods, so if you basically got it flipped, but you project with UMAP, you see that they preserve global structure a little bit better than if you do that with t-SNE, who really distorts the map. So you have to be very careful about that when you're making interpretations on the reduction methods when you're using this type of things. And so in molecular biology, there's kinds of experiments that basically you take one cell, one tissue, so a bunch of cells, and then you sequence everything that every cell has. So you end up with this very, very big matrix where you have each cell that you have a lots of genes. And the t-SNE and UMAP are really used on this crucial step here that's trying to reduce this thing into something more manageable, more tangible, something that you can actually use so you can actually understand what's going on in this experiment. It's very used in this field, and there are a lot of things that were built on top to try to solve the problems that we have in this type of situation. And lastly, it's a bit maybe not the first thing you think about, but deep neural networks are also used for dimension reduction. So a deep neural network, it's just you have a layer, and a layer is composed by these different neurons, and you have first input. So the input goes to the next neuron, and each layer it goes through this network, it suffers a different transformation in different type. And it can be activated by different functions. You have a lot of liberty on how you set this network. And basically you can set this network such that you put your input and you receive exactly the same output in that. And it sounds like it's so stupid to do, and why would you even go to the trouble of doing such a complicated thing to have the same thing? And kind of a big motivation to do that is so that kind of here in this bottleneck in this HBA, you have a encoder that's actually encoding your input layer in a lower dimensional. So you can have a dimensional reduction here, that if you have a very complicated problem that's not easily solvable by any of those techniques, you can tweak this network to do so. And I guess the most classical problem or example on this is on computer vision. There's this big data set of hand-drawn digits, and you can build this network. So you have an original input, you encode it, and then you have a compressed representation of it. And you can actually use this compressed representation to try to classify and build models on your data. So it's pretty cool to do this like this. And you can even use that to add all types of crazy things, even on this type of architecture. If you have the basically a lower dimension here, you can add new outputs on it that's not exactly the same. So you can, for example, start here with a black and white picture, extract the features in a lower dimensional space, and your output layer actually colorizes the feature. So there's a lot of variability on this. So finally, the same method on a different data set. So this is MDS, this is PCA and t-SNE, and you can see that they have actually very different results. So we don't really know, most of the time, we don't really know what the truth looks like. So it's worth to investigate how this behave, and if you have some type of predictive modeling or a specific task at hand to measure how much actual information and how much of the structure you are preserving in whatever dimension reduction you are doing. And another thing, this is compares a lot of different ones that we haven't talked today. And if you have a lot of data for this data set, about 200,000, a lot of them, they just crash. You cannot run them. It takes too much memory on the computer. So that's also something to have in mind. And honestly, they have such different representations too. And to me, it's mind blowing when I look at a picture like this. So takeaways from this section, dimension reduction, it's a complicated task. It's not very easy. If you're doing this for some sort of modeling or prediction, cross-validation might really help you here. Every day there's some new thing going on there, especially in regarding to deep learning. Have a lot of advancements on that. So maybe if you have very specific tasks, it's worth checking out if somebody has done something on that sense. There's no method that's superior to them all. They all have different assumptions, and they all give you a different structure to it. It's really context dependent on the type of data question you have, or maybe underlying structure of your data. And if you have something that's well established, you're trying to establish something new, then benchmarking really plays a big important role there. So do you guys have questions regarding the methods? Is something that's not clear? If not, we can move on. So I guess I'm gonna do another pool. So questions, so very good. Oh, we don't have a question. I launched the poll. If you guys could please answer that in the poll section, so we could know how we're doing so far. And also, if the rhythm is okay, is it going too fast? Okay, good. Thanks, Jean, for the compliment. I hope it's useful to you guys. I think it's nice to keep those things in mind when you are going to code, because those little assumptions in the end, they end up being the parameters you're trying to run, right? The parameters you're trying to adjust. So it's good for recap. Okay, so far so good. So we actually have going to present the data, and if you guys are tired, we can take a break now. But you guys seem doing okay, so I'm gonna do it as planned. Okay, so I'm assuming no break unless nobody manifests that they really need a break right now. And okay, no manifestation, just gonna push through it. So the data that we're going to use in the first part comes from this data set that's called Beans. And I'm super biased because right now I'm working with computer vision, so I do a lot of trying to segment stuff in image. So basically, somebody took pictures of beans and they managed to segment each individual beans. So in image segmentation just means you know that this part here of the image is a bean. And once you know what it is, you can calculate features on it. And somebody was nice enough to do that for us already. So you have the area, the perimeter, the convex area, the roundness of it. So we have a lot of these features that we are not really interested in them. We're more interested in reducing them. And I'm gonna start that. First, I'm gonna do a little introduction to tidy models, and then we're just gonna code. So I hope you have your markdowns ready. So tidy models is this really cool package that allows you to basically build this kind of model workflow without needing to do it step by step in calling out to different packages that sometimes give you very different results. Like some packages might give you a matrix and another one is requiring a list or a data frame. So tidy models kind of goes on top of that and solves that problem. So the way we see that, we have the data and we actually have the models. So the formula or the relationship you're trying to model here. And then we have the pre-processing inside your workflow. So inside the natural process of modeling or building your models in general. I think it's a very smart choice because the type of pre-processing you do and the models that you have, they're really interdependent, and sometimes you have the same model and a different pre-processing. So in that way, each of those combinations become a different workflow, and this makes it easier to work with and in practice. And then you have your fitted results. And each step of this uses different package to configure a different function. So in this case, you're using the beans. And for the principal component analysis, we have this package called recipes. And it's a recipe, just like it's a recipe for the kitchen, you have the step-by-step things that you are interested in doing. And then from that, you can parse anything here through Parsnip. It's a really cute name. They all have such cute names on this thing that has all the models you have. So it has your classifier, it has your linear regression, whatever it is that you're really interesting, it's there basically on Parsnip. And altogether, when you combine a recipe and a workflow, a recipe and and your model, you end up with this workflow. So you end up with a model that groups these things together. And it's very useful because then you can assign data to it, or you can retrain data to it. And it kind of allows you to have this thing in a place that's all together, and that also makes it more manageable to use. And from that, you end up with this fitting model that you usually do some form of metric. So you want to know if it's a good model or a bad model. So it comes from this package called TR-Stick. So altogether, all these things, they work in practice rather well. And this is what we are going to do in the first section. We're just going to see how this works in practice, and we're just going to load this bean data. So I have my RStudio session here, and it's going to be a bit of live coding with you guys to see how we are. So my question is, do you have this C1 student? You have this markdown with you, and can you open it in RStudio, or if you use the command line, you can do the same in the command line too. The markdown, so that it's easy to have a step-by-step process of it. So, okay, everybody has the markdown so far. 12. I'm still installing the package. It's okay. If you have any trouble with the packages, let me know. Some of them are a bit big. And it takes a while, but we have time. Okay, no, one no. Okay, we have most people with yes so far. Is it the one who, it's Jeremy? I don't know if it's Jeremy or Jeremy. Was it you that, okay, Sylvie is done. So, was it either Sylvie or Jeremy who responded no? Do you have it now? Did you find it?
No, it's not me, someone else.
Okay, good, thank you. We are leave no man behind, the person who has not marked out pieces.
If I can't find it, I wouldn't be installing the packages.
Sorry, I couldn't hear you. What can you not find?
No, if I can't find the markdown file, I wouldn't be installing the packages.
So you were not able to install the package, is that it?
No, I am still installing the packages, but I found the markdown file. Yeah, I'm installing the packages for the markdown file.
Yeah, I think yeah, it's a bit like coding, it's a bit like that. You have to take time. So the markdown is on my GitHub. It's there. I just resend it on the link. You can download the entire thing. And if like at before each break, I'm gonna give you a markdown with the answer. So if the installation does not go through that well, we can catch up on the break. So are you good with the installation? So if more people are having the same problem, then we will know. So I also open one. So if you're not good and you're still installing stuff, please also let me know, so I know how to wait for you. Okay, but Okay, we still have some people installing. Okay. Okay. Can you guys see my RStudio window? Oh, this was so useful. Okay, cool. Loading. Okay, cool. No, I'm so confused. Half of you can see it and half of you cannot.
I see it now. I didn't.
So you can see if I can see if it's open right now. Can you see it?
Yeah.
Okay. So basically, you can see when I have the window open. Now you cannot see it, right? No, now it's good. I don't know. I don't understand technology. Literally that meme of stop thinking programmers know how to fix stuff, because I don't. Okay. So see it just like for me is to know if you can see now. See now too, it's up for me. Okay, the thing is I cannot open the chat and have the screen open at the same time. So I'm open here now. I just need somebody to go to the audio and say it's open. Please tell me you can see my screen.
Yes, we can see it.
Okay, good. Okay, I just loaded the packages. So I'm gonna start, and we have some minutes towards the end of the section. And if anybody has some problems spelling and stuff, you go back towards it.
I actually have a question regarding the function, this tidy models _ prefer at line 16.
At line 16.
What does it do?
Oh, okay. So basically, some functions, they have the same name, but they are different. They are different functions coming from different packages. And you can really even open the help here. So basically, tidy models prefer, they solve, it's a quick way to solve this conflict. So when you execute this function, it basically masks certain objects from other packages, which might be a source of conflict. So it's really useful, especially like, I don't know if in this current version of tidy models it's the same, but there's some package that does some subsampling. And if you had that package loaded and tidy models loaded, it would always create some sort of conflict. So this is a quick way to solve it. Does that answer your question?
Yes, and because I saw the warning messages, especially the stats filter and the dplyr filter, which is quite a common issue.
Yeah, and I really like this function. I think on practice, when I have issues when I run it, it works well. Good. So we're just gonna load the data set. And I really like this schema R package, but it's not required for, sorry, I can type. It's not a requirement. It basically just allows you to scheme into your entire data set, and it's quite easy to have a summary of the data. So the name of the data set is beans. It has 13,000 rows and 16 columns, and one column is the factor, which is the class. So if you put beans class, levels, you viewed the levels of it. Oh, a quick question. Is everybody familiar with the pipe operator? If not, just really catch up. If you have this is equivalent syntax. Basically, the pipe just has a quick rate, so you don't need to write something inside of something inside of something. You just pass this as an argument to this function, which make the syntax a bit more straightforward. I think it's a very common practice in R, but good with pipe. Okay, cool. Okay, cool. Yeah, so basically this is our data frame, and it's really really ideal because there's no missing data and has a complete rate. However, if you look at the histogram, you can see that a bit skewed. So here I'm proposing we take a quick look at the area, but if you want to look at something else, you can do that too. So I'm just going to do that. You always do this, and it's never the right thing. So you can see that we have this weird shape that has a high area here and then a second peak here. And then this is the function from ggplot. Is everybody good with ggplot? Two, let me check the chat. If not, I'm just going to do a quick syntax review. So I'm basically taking beans and passing here as the data argument. If you look at the ggplot function, it's a ggplot grammar of Carfax. So the data is the first argument which I'm passing, and then I'm just mapping the area and doing a histogram on top of that. It's really quick and easy. So something, a type of preprocessing that I think is very easy to do when you have this type of distributions is try to log scale it. So if we try to log scale this, we can see that it does not solve our problem. In fact, it just makes this like inside peaks a little bit more normally distributed. So we definitely need some preprocessing if you want to use this data frame on our PCA, because PCA data needs to be centered and scaled. So that's definitely something that we have to do. So let's do it. So first on the tiny models. So it's very common to have this training and testing if you're building a model, especially in the context of statistical learning or machine learning. So they have this initial splits function. So initial splits comes from resample, and basically you can pass your data, and then you can pass a proportion of data that you're going to split to. So we're just doing 0.80. And what's interesting, sometimes you have unbalanced data sets. So data sets where your classes are not equal. You can pass a value here and it will do stratified right away. If we in our beans, we can see that that it's horrible because I made the font size bigger and then it's missing. But you can see that they are not horribly or terribly unbalanced. I mean, this one, it's definitely the majority class, but there's no class that has like 300 or something. So it's pretty okay for us. And then once you have this thing, and you can just execute this code, you can see that initial split actually gives you, bin split gives you this split object where you have which part is from the analysis and which part would be access. So analysis is your training and access is your test and your total data. And you can see on bin train, bin, that's exactly the case. If you do this, you have exactly that, and bin train is now a table that is just a regular one. Maybe that's open it to be quite okay to see. So just a regular old table. That's pretty simple, not that complicated. Okay, no questions on the chat. That's good. So we start you start using the recipe. So basically, the recipe object it can be just a recipe. You can declare it on its own, and then you can add on top of that later on. But you can actually just use the arguments you have. So for instance, here I'm declaring a recipe. So this is my formula. And basically, what I'm saying here is I want the class to be my outcome, and I want everything to be predictive to it, regardless of type. And for my data, I want to be in string. So if you do, yes, I'm gonna do all the titles in the tutorial. So if you do that, you end up with this recipe object, and it's very simple because we don't have any pre-processing on top of that. We're going to see one in a little bit that's a bit more complicated. Now it's really just to get familiar with this function and just know that it exists and then we can do. And then from Parsnip, we can build our model. So I just do just a random forest because it's quick and easy, and it doesn't require a lot of pre-processing on its own. So we don't need to do anything. So right now here, I don't have any extra parameters, but I'm actually going to make the number of trees quite small. So if you don't do that, it's going to take a little more time to fit your model because usually it gives you a little bit, it gives you the number of trees to be a little bit higher. So with this, it's going to be a rather quick model. So what you do when you call a Parsnip model, for instance, on a random forest, is that you choose what type of mode you are. So this even accepts unknown mode, which, okay. But in this case, we just have a classification problem, so we can just pass classification. Or if you have, if you're going to do a regression on random forest, you can do the same, just pass classification here. And then engine, it's actually what is the package that it's going to do this for. So they have all of these packages that you can source it as a method of estimation. So it's pretty cool because if you want to compare two packages, or if you want to do something that comes from Spark and something that comes from R, you can do the same, just using the same syntax, which is pretty good. It's going to be a problem. So if you do that, you end up with a model, and it gives you just what it is, your computational engine and your arguments. This is a list, so you can even carry it as a list. So here you can see that I did not specify mtry, so it's new. I didn't specify the minimum number of nodes remaining, so that's also null. And then finally, you can build your workflow. So remembering workflow is the container object that aggregates everyone. And if we look at it, it's pretty similar too. You can pass it with arguments, but I think it's rather easily to do it like this. So you just declare a workflow, and then you add a recipe and you add the model to it. So if you do that, you end up with this object. So you can see that you have a preprocessor, which is just a recipe that has no steps. It just knows the specification of the formula, and you have your model on it. So that goes back to the quick talk that we have. So we have the recipe, which is the preprocessing, and then we have the model, which is done by your Parsnip, and our Parsnip, we use the random forest. And altogether, this, I don't know what I did there, but altogether this creates that the workflow object that we did. So before I move on to fit this, does anybody has questions? Is there some syntax that's obscure and you do not understand? So I'm gonna open a poll. Are you up to date on where we are? Yes or no? If you have any questions, please go ahead, because I feel like it's gonna be a good timing so we can answer them. Okay, we're good so far. Cool. 20. Okay, good. So finally, we can fit those two objects. And when we first do the fit, we actually do the training. So we are actually fitting our model. So that's why this object's being passed as being trained, and we can do the same. And this is going to be a case where fit exists in a lot of packages. So yeah, it doesn't really have other argument pass-through methods. Yeah, the documentation doesn't really happen in this case. But if you fit an object, it's going to take a little bit. Okay. So you fit your object and you can see that your recipe, your actually your workflow changed. First thing it's going to tell you it's trained, which is pretty good. So there's no confusion if you forgot to fit it or not, if you have maybe it's less intuitive. And then it's going to give you actually the specification of your model results. So if we just compare to the workflow that we created, we can see that the results are very different. So this one's not trained and it does not have the model specifications. So in this case, you have the call that you make, and then you have the sample size that comes from the training, and then you have the number of tries, the split rule. Do we have a question? Yes? No? Okay. So you can use this fit object as a list. So you can, for instance, trained. It's going to give you if it was trained or not. And if you do fit, it's going to give you more information on the engine itself. And if you're doing some predictive modeling, you can even, if you have a model that's working well, you can even retrieve the specifications using this. It's not really interesting to us, but just so you know. And then finally, to get your results, you use either predict or argument, and it's your test case. So on the predict, it really just predicts your data. It just gives you what class I think it is. And the difference on the argument is that it gives you your other parameters with your data. So it's basically pretty straightforward too. And then finally, from the yardstick package, we can, for instance, we can calculate the recall. And then for instance, we have a multi-class problem. So that's why our estimator is the macro rated. It's weighting the estimator for each individual class. So this ends up being it. So that's basically the typical flow of a guiding model usage when you're using a model itself. So actually, we're going to do some pre-processing on our data, which is our first goal. So first, we're just going to start by actually building the recipe, and it's going to be the same as usual. The formula, and that's going to be equal to the else equals everything. And data here, we actually want the whole beans because we are not going to do any predictive modeling today. So we're going to process our entire data and just try to do dimension reduction so we can learn to reuse the packages. So from that on, it's kind of what I'm proposing to do is that we first remove the zero variance from the data. It's also nice because in this case there is no zero variance. But in general, if you're trying to combine these transformations, this is pretty much a case of feature selection. You're just removing something that's not informative. And in this case, it's fairly simple to do so. So the function to do so from tidy models is step ZV. So it's step zero variance. So we can add it, and we don't need to pass anything. We can just all numerical predictors that have zero variance is going to be removed. In our case, it's a bit redundant because we only have numerical predictors, but just so you know that this existence is pretty useful. And then because we already know that some of the histograms that we have, they are bimodal in nature, we can do this step order norm from normalize that basically normalizes by the quantile. So it's really good in this case. And then finally we can center and scale the data. So there is both a step scale and both a step center. But if you want to center and scale in one go, there's like the step norm. Normalize. Let me just check because I cannot remember right now if it's step normalize or it's step norm. Yes, step normalize. So it's just center and scale of the numeric data. Just pretty easy to do. So there's not so we're just going to go ahead and create this recipe, and we can take a look at it. So compared to the other one, you can see that it has operations to do. So it gives you information on that. And I think it's pretty cool to have it in this type of things, because if you do this by hand yourself, you end up with those huge data frames that you are mutating, and then you end up with 100. Not 100, I'm being a bit exaggerating that, but you have 30 columns and all type of things that you did subsequently, which sometimes is easy to get lost. So this is good. And then finally, we can use our recipe. And basically for a given recipe such as ours, the syntax is a bit different. So instead of being a model, we're actually going to prep. So I'm just going to go back a little bit to the slide so I can give you, stop presenting. So I can give you a little bit of more of a feedback, of an idea on that. So basically what it does is that you create a recipe and then you prep it. There's like a wood in the kitchen. So you just take everything from your recipe, you cook real quick, and then you put it in the oven, so you bake. So it's really the equivalent to fit because you have no model. So you're just preparing your data. And then from bake, what happens is it's actually taking the steps that you calculated and applying to your original data. So I think the analogy really works here. So you have a recipe, you have the steps that you take, but it's not going to give you your final preprocessed data yet. You have to bake it first. You have to put it in the oven. So this is really the analogy to go. So stop presenting that and let's go back to the code. So if you prep your recipe, you're gonna have a different recipe. And basically the difference is that it's gonna tell you that it has been trained. So it's gonna tell you the steps it takes. So you can even do beans rec prep, and you can tidy it. And you can have each step that you're doing, and you can carry it by the ID. For instance, the step, it has no step, it has nothing that was done. So if we do tidy, actually you can type, it would be easier than type all of that. Oops. Yes. I'm gonna give you that. That's not what I wanted. But we're gonna do that later anyway. I'm just stepping ahead for now. But you can carry basically the recipe. And then you can have information, which type of variable that you have and what was its role in class, and you have it as an outcome. So you really have a lot of information in this, in the same object, and even the steps. So the steps is kind of what we were talking about earlier. So if you tidy, oh, all right, got you. Yeah, no. So sorry, I forgot the syntax I wanted, but I'm sure that it's in the tutorial somewhere. So basically that's it. You can explore a little bit on your own there. And then finally, if you want to get our recipe back, we can just finally bake our data. Oh, sorry. When you bake your data, you must remember to put new data equal null, or you're gonna have an error. Basically, what happens is in the there should be another function instead of bake called juice, and juice is what you used to use when your object didn't require new data, and then that it was superseded in another version. So bake, you always have to put new data, otherwise it's gonna actually trying to find a data object that you do not have. And then finally, we can look at the previous plot that we had. So we had this lambda, which was not balanced. And then we can see that we have a normalized histogram now, which I think is pretty cool to look at. And you can do the same scheme that we did before for the beans. So scheme and then beans processed. You can see that the standard deviation is equal to 1 for everyone, and the histograms looks pretty normal. Okay. So this is the end of the first section. So are you guys good? Are we feeling? Is it too fast? Is the rhythm okay?
Hi.
Hello.
Yes,
Did you manage to follow?
Yeah, I have some questions to ask.
Yes, go ahead, please.
Yeah, the first one was the baking part where you put it the new data. So can I just put the new data to be just beans instead of now, NULL?
Mm-hmm. Yes. So let me. Here is this part. Sorry.
Yeah, this part, right? Okay, because we use beans for the pre-processing, like can we use back beans again for the new data?
Yes. Exactly. What happens is that it just calculates your data. It does not apply it to it. It just calculated the order and the centering, but it does not apply to it. Training just means that it calculated it. So for instance, in the operations that you have the 0 removed, it means that it didn't find anything to remove, but it has not been removed. If you look at beans remains unchanged. You can even compare with scheme and do int. You see, you still have different standard deviations. Your histograms still look the same. You just calculated it. You did not apply it. It's like a two-step process. So training in this case just means it calculated but not applied. Is it clear now, or is it still a bit confusing?
For me, it's all right. I just see bake as like producing the results. And my next question is, the bake seems to be performing all 3 steps for your pre-processing stage, right?
Yes, it does them in the order you declare them in this case. Like it does first the zero variance filter, and then the norm, and then the normalizer.
So if I just want to see like the results of just step CV, I have to create another recipe that just goes up to steps underscore ZV and then do the baking.
Yeah. So I'm sure that it's an easier way to do this, but maybe, yeah. So in this case, we are just looking at the first one. Just again, I'm sure there's a pretty way to do it, but this is the only way I remember at the time being, and I don't want to waste much time in this. But you see that there's no step and no roles, even if it's trained. And if we do the same for our second one, you end up with this transformation on area. Oops. So 1, skip false, 2, norm, 3, all numeric predictors. Okay. Train true, and is it turns? No. Oh, there we go. So, okay. So just so we know, we are just on the steps and we are looking at the second element of the list there. So if we go step by step, you have your recipe, you go in your steps, and then it's going to give you a list. And each element of the list responds to the IT you have. So we're going to choose the second one, which is our order norm, which is the information you have here. And then finally, if you have your transform info, we're going to give you step by step. So for instance, for area, you have the original quantiles and the original values for each original quantiles that you calculated. Is this more or less what you were looking for? Or does that not help you whatsoever?
Okay. Actually, I was thinking of just doing one pre-processing step and then I bake it, and then I update another pre-processing step and then I bake it again. But I guess this works as well.
Yeah, because it's gonna apply basically at once, right? It's not gonna apply it term by term. In this case, you can, oops, sorry. For the third one, you can look at the means for each one because you're recentering. So it's gonna depend on each step that you have. And it takes a little bit of getting used to this. And especially if you are looking step by step, it's not something, personally, it's not something I do that often. So it took me actually like good minute to remember where it was. But it's a good reflex to look at them and receive like what's changing in your data set. It's good reflex to have. Do we have more questions? I'm not sure, so okay.
Would you mind to share just the completed file? I might also just missed one step in the process.
Yes. So I'm just gonna put on the same GitHub.
Okay, that would be great. Thanks.
Upload like each end of the section. I'm gonna upload a file. Sorry if it was that quick. I'm gonna slow down as we go along, so everybody can follow. So I'm putting both a HTML and a RDM, and it's called S1 underline answers. Okay, so, okay, somebody asked me to scroll up on my code. Is there some code that I type, or was it in the Markdown? But the point of this was just normalize the, yes, exactly. So it's just to normalize, it's just, you can use those recipes to normalize your data. And once we have that, we're gonna use that to do the dimension reduction. So this is just so we can get our data and our thing running, because once we have it, we can just reuse it all the time.
Okay, but I have another question is that I
Yes.
understand that this step is done before your dimension reduction, but I also see that the recipe uses the class variable. So I usually like in these kind of cases, we don't know which class each data belongs to for like this kind of exploratory dimension reduction. So is it possible for recipe to not take any class and still do the pre-processing stage?
Yes. You can do that and pass no formula, I guess. We're not doing that. This is not on the tutorial. I think that, but you can definitely do that. You can just use it to way to pre-process your data and see to have it in this thing. I think it's more also dependent on the context, because tidy models was created so you can have so you can build models. So usually when you are model building, we are considering with an outcome, and then in that although in this here we are using for dimension reduction, you can easily just add a model on top of that. So in a way you can sort of understand why would you want to keep that. But I think it's just a matter of the usage of the package in general. Okay. So do you guys have more questions? Do you want a quick break, or are we feeling good and energetic? So I'm gonna add the poll. You can have a 5-minute break if you want to. Quick break, please. Okay, the people have spoken. So I'm still going to be here. So if anybody has some problem and wants to start during the break, so it's let's meet. So to me it's 7:20. It's 17:23, so 5 p.m. So let's meet, if I'm 23, so let's meet at 5:30. That's gonna be easier than just 1 minute difference. Is it good for everybody then? Okay. Okay, everyone. See you guys in a bit. Hello, everyone. So I guess most of us are back. Which I do realize is a weird question to answer, because if you're not here, evidently the answer is going to be no. If you're already here, and this section we're just going to do the PCA and the ICA, so you can just open the S2 students markdown I sent you. And actually the first part right up into the section 2 is what we already done. It's going to give you the same process data frame. Just as a recap, we just processed the data frame. So now it has been normalized. So it looks like this. Back. Okay, cool. So I guess most of us are here. So I guess I was typing too fast. So I'm going to try to slow down on that so we can be all on the same pace. Okay. So this recipe right here is the same one we had before. So beans reg prepped is the one that has been trained, but that it just been trained. It has no data on it yet. And now it's going to be kind of interesting because you can actually just add one step here to do our PCA. So you can just add step PCA, pretty straightforward function. And it's going to do the same thing. So I'm going to open the documentation. So basically, you can choose the number of components you have. So I'm going to put, let's put 5 or let's put 6. And you can, for instance, if you're doing some modeling, you can choose if you're just going to do PCA on the training and not on the test set. But that really doesn't matter to us here. What really matters is just the first argument, which is all numerical predictive. And I'm not going to execute this code here on the main screen just yet. I'm just going to show you here on the side. And okay. So sorry. So if you do that, you see that I'm actually gonna edit this thing. So we can see that it has not been trained. And if you are doing something like this, it's nice to check. So in our case, everything else has been trained. It comes from the recipe we did before. And just this one step of the PCA has not been trained. So that's why right here, I'm telling you, do not forget this step, because otherwise you are going to be baking something that it has no point. Like we already done that. What did I do wrong? Can't rename variables in this context.
After prep.
Oh, right. Sorry. No?
It's
Between
the-
prep and the parentheses.
Oh, right.
Yeah.
Thank you. Thank you. Nope.
It's the variable k equals to 6. It's supposed to be
Oh, right.
memory.
The what is it supposed to be?
It's
Component.
a scroll, a stop. Yeah, that one.
Yeah, there we go. Okay, good. Thank you, everyone. Sorry. Okay, now we can see that it has indeed been trained. So So we usually want to inspect a little bit so we know that we have the right number of components, and 6 is just not a random number I'm putting here. So to do that, we can do kind of what I was doing before. We can filter this step ID, and then we can tidy this recipe, and we can get the variance out of it. So it's going to execute this first part out of this, so you guys can see. Nope, my copy and paste is not working. So it's pretty much similar to what I was showing before. Okay, and then I'm just basically filtering out the steps that I want, which is here, the PCA. And then if you tidy the recipe and look for variance itself, yeah, sorry, it's gonna give you this big table that has a variance, and like variance, the ID of your recipe, your component, and the value. And if you remember, we just asked for 6, and we can see this is a much bigger table. It has 64 rows. So actually, it's nice to check that. So we can see that. So we can see that has all the types of variance. So we have 4 types. That's the variance, the cumulative, the percentage, and the percentage cumulative. And if you're a little bit familiar with this type of analysis elsewhere, you kind of already seen this plot where here on the on the Y, in our case, we have the percent of, oops. Is it not Y or is it lab Y? Oh, sorry, there's not an underscore. Okay, so we end up with this. So you have the percentage of variance that is explained by each component. And the idea is, because you have this kind of plot, we can kind of elbow out the first 3 or the first 4. And then we see that after that, the components, they really don't explain a lot of variance. So we just want to keep the number of components who can explain. And if we go back to our original motivation, we go from having like 16 features to just looking at just maybe 4 or 5 components that are more important. Is this clear for everybody? That do we have questions regarding this so far? I think you want to run and show at the same time. Yes. Thank you. Okay. Does anybody have questions? No? And you can do the same for the cumulative variance. So let's do the same. And you can see this is exactly the same thing. So you can see 5, it pretty much explains nearly 100% of the variance that we have. And from that, we can inspect how each of the features that we have actually makes for these components that we have. So basically, this being stated is just the value for the components, the table that we just showed. The only thing that we are doing a little bit different here is just that we are ordering them. So the number here is, we can put 4. Basically, we're taking the components in 1 to 4. This is what this is doing. So based here is just creating this list, and I'm just carrying the component in this data frame here. So I'm taking all the components that are in this list, and then I'm ordering them according to their components, and we can face-it wrap. So we're going to split the plots according to them and according to the values that they have. So I think it would be nicer to look in a big screen. So we can actually look how each of the features that we have are part of each of the components that we created. We can put it, for instance, the extent is not really important here, and then it has a big value here on PC4. Is everybody here?
Hi, question. What does the value means in this graph? I'm a bit lost.
The value, it's because when you're generating the component, you are fitting this line, and each of the features, they are basically being fitted to. It's basically like if you have a big. I wish I had something like a whiteboard to write on. Basically, if you have components, you are fitting a given value, which in this case is your eigenvalue, and a term that's adjusting it. So basically, the value is that So it's how much each of that feature it's important or relevant for that component. So if we can imagine this component, the value is how much each individual aspect is contributing to explaining this variance, the variance that's summarized by this component. Is that clear or no?
Okay, I just see as how much the variable contributes to the PC. So does it matter if it's negative or positive in value?
The negative or positive is because you're projecting into. You can look at them in terms of absolute value, but it just gives you the direction of the components, because you can imagine this component as having a certain orientation too. And there's another maybe that would be a bit more intuitive to see, which is the other plot that gives you it gives you the same information and with fewer lenses, but just looking at the absolute value of the contribution. And then you can just look at the sign and see if it's contributing positively or negatively to each of the axes. But it's more or less the absolute value. It's how much each component is associated or related to a given feature. It's the plot the plot that's showing, not on the markdown, on the screen itself. Is that a bit more clear for you? Is that less counterintuitive?
Yes, the second plot looks better.
Okay. I really like the one showing on the markdown right now, but I think the second one's it's easier to understand, I think, and it summarizes information maybe a little bit better. Okay. So are we all here? Is it better now? Can you guys follow what are we doing? So is the rhythm okay? Is anybody stuck? In need of assistance? Is it possible to draw precise correlation cycles within the tidy models framework? I think it could be possible, yes. I never tried to do it. But the thing I don't remember is how do you start that plot? But so basically, I think so. I think you could do it. I don't know how to do that by heart. I can do that after the session and put it on the same repo if you're interested. Because I don't think we're gonna have time to do that after. And so just to make sure I heard correctly, you push the answer version of the Markdown to take it up after the session. Yes, that's correct. Yes. And I think it was Antoine Bichat that answered the correlation cycle. If I forget that, you can write to me and I'll do it. Okay, Iridium is fine. Good. Finally, we took a look at the components, but we don't have our transform data yet. So we need to go back all the way so we can get our PCA recipe that we prepped. Remember this? I'm just going back to get the name. And then we bake. And don't forget the new data. Then we finally get our PCA components. And then we can look at them. But maybe it's share via the plot zoom function. And then I'll change my screen sharing. So stop presenting. Then I'm going to share the window. The thing is, I cannot share the Zoom window on here, apparently. I can only share if I show the entire screen. Okay, but what's going on? Now you won't find my RStudio. But basically, you can see each component against each other in that plot. Jesus, technical issues. I'm gonna share window. Okay, I'm gonna share my entire screen because I cannot share. I cannot find the RStudio anymore. So basically, you have each component in each axis, and luckily, you can zoom them. Mine's not working, but we can zoom in those features and see which one we can sort of better understand or better separate our data. And this is the next plot, the plot we are zooming in, which is the PC1 and PC2. So we can kind of separate between the different types of beams according to the components that we have. So we can kind of see some separation between them. And if you were interested, for instance, in generating some sort of clustering method based on this might be interesting to us. And we can compare them in this way that makes more sense. And that's kind of it for PCA. Does anybody has more questions, or stop presenting so we don't have a myriad of things? Okay. Oh, you guys are so much quicker to answer than mine. Oh, you're using the wrong data. Yes. Were you using the other one, or do you want to share what happened? Are you okay now? It's you to manage that. Okay. So the next part is the ICA. So I'm gonna show you the function, but the idea is that you can do that yourself a little bit. So once you have the plots are ready to go, so we don't waste time on that. So basically, it's the same thing that before that we did. We're just gonna use the same preprocessed data that we have, and then the function for the step ICA is this one. It's called the step ICA.
We don't see your.
You're not.
No,
Oh
with
my
your.
Oh no. Okay, I don't know what's going on. I'm gonna refresh my page. I'm not be gone. I'm just trying to solve this. Okay, do not panic. I'll be back. Hello. So let's see if that fixes our problem. So can you see my screen?
Well, we see your web browser.
Oh, you're seeing my browser and not my screen. Oh no. Okay, stop presenting. Share options. Okay, now you see my screen.
Yes.
Okay. I don't know what's going on. Sorry. Okay. So did you see the plot? We were discussing this plot with the components, and then we zoom in here so we can see in each component, and we can sort of see some separation in them right here. So I guess I was telling that you were not seeing this, that this is the components that we might be interested if we were, for instance, building a classifier or a clustering method. We might be interested in looking at these components because they look promising. And then this next part, like the functions, they're very similar to the ones that we used before. And the idea is that you can try to run this on your system without me first. And then I've just showing the function that does the ICA, so it's just step ICA, and it's pretty similar to the one before. And yes, we can maybe have some time so you can try to create this recipe yourselves. And I can help you guys as you go along if you have questions. I saw that the data was a source of confusion. So I'm just gonna go back to this. I think this was where there was some confusion with the baking function. So you're basically just performing the things you just calculated. And yeah, please don't forget to move. Okay, I'm gonna put on the GitHub repo the tutorial, the section, because I think it might help you with the ICA part. And I'm gonna create a poll here. Oh, okay. I see. Yes. You have to install. Oh, sorry. Yeah, you have to install first. I see. I think I must have forgot to put in the section header. Yes. Fix that. Gonna fix that in the other one too. Okay, that's good. If you don't get, okay, got it. Oh, I see. Is for the people who are having to install, the installations are quite okay? They're not taking too long, are they? My machine developed quite fast when I checked. Very okay, good. Okay, most people are getting close to being done with the IC. Is anybody stuck? Does anybody need help? Is there something not clear? I'm done with the baking step. Cool. So if you got to the baking step, basically here you have the data. So I'm just gonna. this is the answer. This is also already on the GitHub, the repo. Then you can start exploring our data set. And you can see that even there's no clearly separated, and it really is going to depend on how many components you put here. I also put 5. So it's really just going to depend on the number of components that you decided to put there. So for instance, here it looks like the 4 and 4 has some separation, which is interesting. But 4 and 3 basically. Yes? Do you have a question?
Can you go back up to the
Here?
step,
Yes.
the code for the steps, just for like a minute? Thank you.
No, yes, for sure, for sure. Can you tell me when you're done?
Okay, I'm good. Thank you.
Okay. No problem. Okay, so we were looking at the components and we can see what do they look like and if we can distinguish between them. So 1 and 3, or maybe 1 and 4, or maybe even 1 and 4. It's really going to depend on the zooming in. It's really going to depend on what you choose. You can see that it's not that clearly separated. It kind of just looks like a blob. Maybe you can also try component 1 and component 4. You know, we already tried that. 1 and 3. Especially for this, we can see that we don't have that nice clear separation. So for this data, at least the PCA seems much more reasonable than the PCA. Sorry, the ICA. The PCA seems much more reasonable than the ICA. And we can do the same thing as regarding to the terms, and you can see how much impact or how much value they have for each of the features. And that's kind of it for PCA and ICA. I think it's pretty okay once you get the hang of it. It's just a bit of the syntax and a little bit of I think the most. Well, here we have the functions for plotting ready to go, but this part itself, it's really the part that matters for us here because it's the part we are interested in learning here. It's really the how do we create this recipe and how we create the dimension reduction method we are interested in looking, and then how do we get the stats, and from them how do we get the actual data from it. So is everybody up to speed? What is resolution method fits the data better? That's depending on the goal you have. For instance, in this case, we don't really have a particular goal in mind, but if you had a classifier and we were trying to classify them, then we can just process them, build a classifier, and see how the classifier performs. If we're interested in data visualization, for instance, then you can visually inspect your data. For other methods that we are going to discuss later today, for instance, the UMAP or TSNE, you can calculate in the original data what were the neighbors. And then that gives you a metric of the distance between the neighbors that were really close or neighbors that were really far away. And the next section, we're gonna see yet another metric. So there's not really a super defined criteria to say what is the best way to access it. In this case, it's when I'm saying it's better, the PCA it's a little bit better. It's just because here this doesn't, at least for the time being, like this does not separate our group of data into groups as the PCA did here. So we can kind of see blobs. So in a way, I'm just saying, oh, I want to have a nice data visualization of how the components are separated in each beans. So PCA seems to be a little bit better at that than the ICA, but a firm criterion to access that. It's really dependent on the question that you have at hand and the method you were using. Is that clear for you? Is there something else that maybe it's not? I have so just let me know. So we can either move to section 3, which is not going to be with title models. It's going to be more close to the base syntax in R, which is about multidimensional scaling, or we can have another 5-minute break after that. So let's see what you guys prefer. So now I have a 5-minute break. And again, the answers and the markdown are already on the GitHub. Okay, we are a bit split between break and section 3. Okay, so let's have a break then, and we go back in 18 for me, so that's 6:18 p.m. for me. And then we can talk about multidimensional scaling. So for the person who asked about functional PCA, I've never heard of functional PCA in my life. I'm looking at the Wikipedia now. If you don't mind answer, like in which context do you hear that? So we have a Q&A. If I don't see my full screen function. Okay, so we got this very interesting question on the chat about functional PCA. Thanks, June. Particularly, I never had that before. But there is a section on the Wikipedia page that talks a little bit about what it's assuming. And basically, it seems to me that the big difference is actually the space, the type of data that you use. And so if you say it's speech and auditory signal processing, so apparently they have this specific type of data that they are calling Hubert, the Hubert L2 space. So in the end, they are not using the mean, they're doing the modes of covariation, but they still do some sort of eigenvalue decomposition and some inner product, so they use the integral, and they still get some sort of components that are similar. This is so interesting. Never really had the chance to work in that field, so it's pretty cool. Pretty cool question. Okay, so I think we mostly still here. We're mostly back. Just gonna make sure we are back. Yes or no? So there's this we kind of went on a tangent about PCA and functional PCA. So they're talking about basically the difference between the two of them, and it's some of the assumptions that they make. But it's speech signal processing. So this is actually a case that you can combine ICA and PCA. So you have a noise audio, you can separate them. So you can use the ICA first to get the latent one. So it probably has a distribution to speech, or if there's some like tapping, you have a distribution to tapping, and then you can like break down each component based on the distribution that you had before, which I think is pretty cool. So, okay, let's go to the RStudio, and we have most of you back. Okay, so we're going to do multidimensional scaling, and we're going to change the data. We're going to use this data called Swiss. So it's from Switzerland, and it's basically, I'm going to do ahead. It's basically, it's still a really, basically demographic data from French-speaking villages, and they have different features. So there's like fertility, rate of agriculture, like examination. It's the grade that they get in a metric in the army. Education years, if they are Catholic, and apparently this is like either they're Catholic or Protestant. And then you have infant mortality. And the reason we are switching, we could try to do that on our original data, but as I said before, this multidimensional scaling is at least n squared. So if we have a 10,000 roll, that would not be quick or easy, and we don't want to be stuck on this. We really just we're interested in learning these methods today and how to apply them. So we can see that this has some of the data is Q2, but we are not. That's not a huge issue for us because, for instance, MDS don't necessarily mean that the data needs to be centered and scaled. Sometimes it's very good to do that because you might have a lot of variation between the data. For instance, here you can have the very different means. This is not even the worst, but if you had like maybe 210, then of course the 200 will be biased towards it because it has a higher cardinality. So that's something that you might want to pay attention to when you're doing that in real life. And here I'm just plotting something. So you can see the number of education years and this examination score that they get in the army, they have some relation to them, and you can see that they seem like they are correlated. And so does fertility and agriculture. So you can explore a little bit this data set so we just get a feel for it. So basically we're going to do the multidimensional scaling, and there are quite a lot of different packages that do this. And there's this CMD scale one, which is native to R. And it does the classical one, so principal coordinate analysis. And it has quite a lot of different parameters that we can choose. We can choose different distances. And here we're just going to try to do first with the Euclidean. So I think this is going to the default of the function. And then we can try the number of dimensions that we wanted to reduce. So K, so that's also one of the reasons that I got confused in the other one. So maybe we can set K-Put tool here, which is also default. And you can also check if you want to return the eigenvalues or not, or if you're going to try to modify the behavior of the function in any way. And so we can do that step by step. So this is, it's already, you guys already have it. So this first method, the distance, it really just gives you this matrix, which is okay, but call my no. Don't remember how to use matrices. No, but that's it, isn't it? Sorry. No. Can anybody remember how to use Beza? Wait, I have to Google that. Matrix. I think you don't want to forget when you're teaching a tutorial. All right, okay. So I think okay, sorry. That's what the problem was about. It's not syntax. It's actually it's giving you so you guys are, it's giving you the distance as a class object and not a matrix. It still prints, so it's matrix. Okay.
Hi.
Yes. Just give me a
Yeah,
second.
I think it's the next one, this Euclidean underscore MDS is your matrix, I think.
Sorry? You said
The next one, the Euclidean underscore MDS is the matrix.
yes, but this is just, you just get the distance. That's why, that's kind of why we want to show this. So maybe we can do it this way. Okay, so basically just trying to show that the distance matrix, they are always, it's always zeros, and then they are symmetric, not always, but most of the time. When they're metric, they usually are symmetric. And I just wanted to show you that this is the matrix itself. Sorry again for the little confusion. Okay. And then when you do the CMT scale, then it's going to return you the matrix. The Euclidean MDS is a matrix itself, but it's not a distance matrix anymore. Each component is your metric component. So each one of this is the factor that you calculated. So it's not the same matrix. Is that clear? Yep. Okay, thank you. Sorry for the little confusion. PCA Euclideanism will output the same result as PCA, right? Yes. So that will give you the same results as a PCA, indeed. And that leads me to my next point. So I figured we could try this with another distance. The exactly same output, we can literally just copy and paste. and we can choose another distance to run. So there are quite a lot of different distances that we can choose. There's the maximum, Manhattan, Canberra, binary, Minkowski. So my questions for you guys is, which distances do you want to explore? So you guys have a preference? So which distance do we want to try? Do we want to try the Canberra, Minkowski? What else do we have? Manhattan. And binary. So I created a poll, and you can vote which one you want to try. Manhattan, Sweden. Yes, CMD scale takes the distance metrics, and for k equals true, I calculate what the fours are. Where do we see fours?
I think she meant by the 4 distance metrics, the Canberra, Minkowski's, Manhattan, and binary, if I'm understood correctly. The 4 distance in the poll.
What's the difference? Sorry, I couldn't understand your question actually. Can you repeat it? What is the difference? Or okay, so the difference between the 4 distances. Okay, so basically the Euclidean, let me put it, maybe you can, I think the Euclidean and Manhattan are the most well-known. So let's stop sharing the RStudio and let's take a look. And here, so the Euclidean distance is, if you have, for instance, distance between this point and this point, you kind of just calculate the distance, and it's pretty much like calculating the hypotenuse of a triangle. And then like the Manhattan distance sometimes is also called the city block distance, I think. No, that's taxi cab. But sorry. No, yeah, it's this one. Because you calculate the distance between points by counting these grids. So as opposed to the other one, so you see that the Manhattan distance, you're calculating the grid, counting its neighbors. And then the binary distance, and I'm not very good at remembering things by heart. The Canberra, I remembered that I think it's very good at calculating. Yeah, so this is the formula for 2 points. And I think it's, if I remember correctly, it's a little bit less sensitive to zeros. It's a little bit more robust on that end. And I think the Minkowski's in Manhattan normalized in non-vector space. Okay, it's just a generalization of the other metrics, so they should be very similar to each other. And then do we have, yeah, this is the 4 we have left. But it's kind of a very, stop sharing, let's go back to this, our studio. It's kind of a very, just different ways you calculate the distance, and the different, like, the certain distance have certain properties associated with them. And they basically, for instance, if I remember correctly, the L1 norm is very sensitive to bias because it kind of calculates the means of the data, and some are more robust to outliers. So you really have to look at the distance that you have and make sure that the type of the data that you have fits the question that you have. In this case, because we are kind of just exploring, we are not too concerned about that in real life. Sour was super nice. Oh, okay. So apparently Minkowski distance is used in general relativity. Cool. And about the distance function, is it calculating distance between rows where each row is represented as a point in a 6th dimension? Yes, it should be calculating the distances in this total space that you have. So that should be pretty much the case. So do we have more questions? Okay. I didn't realize this would be sort of confusion. So we got the Manhattan distance from the plot. So let's do that. So we just gonna here. We're just gonna do it the dirty way. I have not found. Oh yes, we cannot do that. It was from here. That should be good. So if we compare the first one, which was the Euclidean, with this one, they look very different from each other. I always think that these two should be somehow together because one is the right one and one's the left one. So I found it very funny. Like in my mind, I immediately think that there's like a direction component associated with these two cities. So that's just to show you that you can do that with base R. That being said, I think the carrying or the leading, and let me see if you have more questions on the chat. From the Euclidean usual distance between two vectors, norm. Yeah. Yeah, I think distance in itself could be a thing that we could go on for hours because the way you calculate them, it's very, very intricate and certain properties that hold in certain spaces. It's a very, very good question indeed. Okay, so going back to the vegan package. So this package, it's vegan. It's a package that was made for ecologists, and I see them using all the time. There's a lot of methods that are made for community and community analysis in this package. And some of those methods, they've been optimized for the specific case, but some of them you cannot really find them in other packages, especially this meta MDS function in a weird way. It behaves a bit similar to the tidy models because what this function does, it actually performs this other function, the non-metric multidimensional scaling from Vegan. So this, which you would have to run it, and then you would have to calculate a distance and get the data from it in this wrapper kind of method, which is MetaMDS. So it makes it much easier to run this function. And they have more distances that are available in this package too. So really distance could be a thing on its own. So this is the Jacquardin index, that distance, which is an index of similarity. So you can think about how much something is intersection in between two things over the union. So you kind of have this matrix varying from 0 to 1. So that gives you how similar two items are. But there are a lot of them, and sometimes there are certain tasks that they are very like tailored towards. So that's also something that might be field specific. And then like the another things for the number of dimensions, so which is also okay. So you can, because if you remember from earlier, this needs to converge. You're trying to minimize something. So you need a number of tries, so you can also try that. And similar to that, you can also have different engines. So we are just using the one from Vegan, but later we're gonna see NAS, and this engine also exists there. So it really, it's all on this one function that can help you do that. And if we can look at even at their examples, you can see that it's pretty simple once we have it. So it's gonna execute it, and we can check our MDS. And you can see the output. It gives you the call, you give the number of dimensions and the stress. And the stress, there's not super straightforward way to interpret it, and there's quite a lot of discussion about it. So somebody had a question earlier about how do we define something good, how we define the dimension reduction is good. For multidimensional scaling, stress is one of the metrics we can use. And basically the rule of thumb is that if the stress is smaller than 0.2, you would consider it good. You would say it's okay that you are retaining a good number of dimensions. You're gaining information from that. But for instance, we can check. We tell you that you ran a mono MDS, and we can check that, and that's going to be the function for non-metric multidimensional scaling. And we can check on that function itself. So we can see, for instance, there are different types of stresses. There are different types of thresholds that you can pass to your model. So maybe if you're trying to convert something and it's not working, you can relax the threshold and see how it behaves. So you really have a lot of flexibility in this model, and a lot of things that you can try. And even here you can like see that you can get your points exactly from that. So you have your component, your multidimensional scaling component 1, and your multidimensional component 2. And this is exactly what we are plotting here. This is also from the base R. So this is not really informative for us. We cannot really have a lot of information from this, but it does not look too different from the Manhattan plot we did earlier. So basically we can make that into a data frame so we can get some information. So basically I created this this data frame with the component, but we really want to make sure that those roles are the same. The role in between this data frame and your Swiss data frame are the same, so we can combine them together and try to understand a little bit of what we see. And this is just a sanity check to check that this is indeed the case, that there's not a permutation that happens somewhere. And once we do that, we can try to see if we can find some type of thing. So here, we can delete this for now. Maybe it's too much information. I just deleted the shape here. So we can color according to fertility, and we can see if each of the components can or does have a direct effect of fertility. So if fertility has a major or can be something that can be explained or reclustery from this. And we can do the same for education. And you can see that education, kind of has this a bit of a funny distribution. You can even plot the histogram for it. So this is just the histogram from the base R. So it's very much tail heavy. So we can so that's kind of what we can explore a little bit. So let's suppose if it's greater than 5, you're gonna put in a different color. Oh yes. And then you can see that it's not really has a huge difference. So the problem that we just happened here is because I had this function here that colors the data frame in this way, and because I just made color something binary, obviously I cannot color something binary in a continuous form. So it was just the error we got. But it's pretty easy to run, and it gives you a lot of different types of ways to run. Actually, a lot of flexibility, different ways to design your multidimensional scaling within this package. It's just a little bit different from Tidy Models. It doesn't come with its pipeline or its workflow, but I think it's pretty solid, pretty cool. So do we have questions regarding the vegan package? Are we lost? Are we good? When nobody answers me, I cannot tell if you guys are completely lost or it's super easy. So just launched a poll, trying to keep up. Keith, if I don't know if the session is open at the end, if we can stay longer. But in the end, if there's something that's not clear, and since you're very new to R, we can go over. It's not a problem. Okay, everybody's cool with vegan. So which one do you like best so far? And then lastly is the rhythm. Okay. Oh, everybody prefers Tidy so far. Okay, good. Okay. And then we don't have too much time left here to explore the individual multidimensional scaling factors, but pretty much we can follow the same steps we did for PCA and ICA to see them individually. And this is also for infant mortality with the CTs. And you see that just looking at it, it's a bit hard to see. And it follows and we can check the stress too. For the person, I don't remember your name, that asked me about coordination plots in vegan. I think they have a function that's already implemented for that. I don't remember by heart, but I'm pretty sure it's quite more straightforward to do that in vegan in mass than data in tiny models, the correlational circle. And you can use the same method, just pass a Euclidean distance, it should be the same. It's okay, it was Antoine Bichat. So have you used the vegan and tidy models together, if that's possible? I have not. I never had the necessity to. I don't know if that's possible currently, but that would be cool if it was. It would be pretty cool if it was. But no, I have not used that together. What are the main differences between vegan and tidy models? It's mainly syntax. I think it's syntax, yes, for sure. I think the tidy models has a very general syntax that once you do, you can do pretty much a lot with it. Especially when it comes to when you're trying to do dimension reduction and create a classifier on top of it. Tidy models has some extensors that you can fit a lot of workflows at once. So you can create maybe 10 or 20 different types of preprocessing combined with different models, run, and then just let your computer do the job, which I think is pretty cool. But I don't know if you can automatize that the same way for vegan, or at least I never had to do so. And the vegan, I think it's also very field specific. So if you're someone, I think R is pretty big on ecology. If you're someone who works with data, like from community data, or some problem similar, vegan, sometimes they have this very specific functions, very niche functions for this. And so I think it's very useful. It was designed for ecological data, so it's much more specific. Yes, Sarah said that she can look into it later if R and tidy models are compatible, and what you're going to do and how you're understanding data encoding. I think it's also a little bit of a philosophy, because tidy models, you keep the data where you are and you pre-process data all together. And on vegan, you can pretty much, when you look at this, you pretty much are doing this in one go too. It's not like you are separating them in a process. This is almost like an analogy, and you can even see, for instance, it did some scaling, it did some centering, it did some rotations. I expanded course based on the Swiss thing. So I think it would be really cool is if I don't think there is multidimensional scaling in tidy models as it is. I think it would be pretty cool if it did. So speed is okay for everybody, and okay, good. So we're running a little bit late, so it's going to be a bit speedy now, so we can get to our last session. Okay, the last package I wanted to show you regarding this is the mass one. So mass has this function called ISO MTS. We're going to take a look at that. So it's just one of the many forms multidimensional scaling, and then basically it's just a different syntax for the same thing, and you can even see that basically it gives you your iterational value, so you know which direction you are and the final value that you have for the stress. And I think it's kind of interesting to note, for instance, if I start with a very low number of components with 2, I have a very high stress, even though it's converging, and that's not a good sign. So there's kind of the idea that 10 is a fair value for the number of dimensions, but if your stress is a bit high like this, then you should keep adding more dimensions, and so your stress is a bit low. But is similarly to what we were discussing with vegan, because this method it's so flexible. Because this method is so flexible, it becomes a little bit more complicated. So you have the dimensional here, which is getting the data frame. And then we can plot the dimensions in a similar way that we did for the PCA and then on the ICA. It's going to give you that frame that's very similar. Oops. That's similar to the other ones, and you can try to see if you can, for instance, when you're doing the Swiss, you can try to understand what factors are separating the cities, or you can even think, could I separate the cities into groups, to very different groups? And all that's doable, exploring this type of distance or metric. And I think I think the takeaway message is that multidimensional scaling requires a little bit of exploration when it comes to your methods and which packages you're using. But it also gives you a lot more flexibility on how to work with that. So, okay, and we have more questions. Vega seems to be more focused on dimension distance reduction. That too, I think there are a lot of types of distance that have been created for specific for ecology and the problems that they face. That I don't know other fields that requires or that do that outside of that. Also, I'm biased, right? By training, I'm a biologist who does biostatistics and bioinformatics. So, but even like other domains such as computer vision, I don't see people that do that. And then for the models to process and step back, it's getting from the data. Yeah, I think tiny models, it's pretty step-by-step approach, pretty cool. Yeah, tiny models also does more dimension reduction, but again, so does vegan. This is just one other part of it. So I'm gonna go straight to the section 4 in the interest of time, because if we take a break, then it's gonna be a little bit short on time. So okay, so can you guys see my screen? I suppose so, because I can see my screen on the live video. So created a poll so you guys can check. Okay, got a thumbs up. Very good. Okay, so this last part talks about this new constant influx of methods that are being developed And what if I want to do a new dimension reduction, like autoencoder that was being developed on Python? Can I still do that in R? And this kind of sparks this debate that I see a lot of people, especially on Twitter, that go on threads, and people have very mixed feelings about should you use R, should you use Python, and this and that. And it's a bit, I find it a bit weird, a bit odd, because those are programming languages and they have different communities and different things attached to them. And actually, in the end, you can actually do much better than have these discussions, and you can combine them both. And nowadays, you can combine them with this package called Reticulate that lets you run Python straight from R. And it's really, I think it's really pretty cool. And I think what happens a lot is that sometimes people are used to a specific method implemented on a package in Python, and you really want to compare that with maybe a different method that comes in R. And in the past, you ended up having to do both scripts and then trying to compare them, and it was very messy because you had to send a data frame from one computer to another if you were like running on the cloud or in a different server. And I remember I did this in some projects, and it was super messy when there was not Reticulate. So the fact that you can do this now, it's really cool, and in a day-to-day basis, especially if you have a team of people who work, some work with R, some work with Python, it's pretty cool, it's pretty nice. That being said, there are some things that you should be aware of. R and Python, they have different types of objects and different types of classes in them. For instance, a named list is just a list that you have a name for each element, and that's in Python, that's automatically going to be converted into a dictionary. And so there's this conversions between them that you have to be aware of. And maybe not everybody's familiar with Python, and for this you don't need to be that familiar with. But then if you want to try to use something like this, you can take some time to understand how this works, because the philosophy when it comes to typing of objects is very different between the two languages. And we are changing the data again. And the reason we are doing so is because if we are going to try to do nonlinear methods, so right now we're going to try to tsne and do umap, we really should try to use data that's nonlinear. We are kind of nutsing because we're going to do this Swiss roll data set. So it looks like one of those like Swiss roll cakes. It's this thing on 3-dimensional, and you have a Swiss roll into it with the different colors. And you can see you just trying to reduce from 3 to 2 dimensions, and the colors can give you a pretty good idea on that. It makes it easier to understand than other data sets, I guess, that could use nonlinear methods. So that means we are going to do the data set called Reticulate. The data set's already marked down called Reticulate. And I'm not completely sure how easy this is going to be for everybody, because the Reticulate installation requires quite a lot of configuration. So I'm gonna try to do this, and then we can try this on your end. We only have 30 minutes left, so I'm not sure I'm gonna be able to check with everybody if we can go step by step, but we can definitely try to at least troubleshoot how that's gonna go. So do we have, so I'm gonna open a poll now. So we have questions about Reticulate or Python, or would anybody be, maybe you don't really are not familiar with Python and you just heard of it before, and also do you work with Python, or do you work with Python versus does your team or maybe you use for school? So most of you do not work with Python or never did. For the Python library, you can do pipes down. Yes, that definitely. I think the M1 Mac chips have been a big issue when it comes to installing them. There's quite a lot of, so for everybody who's not aware, the Mac M1 chips, they have been a lot of issues with people trying to install them and Python on them. And it has been, it's been quite recurrent that I think when you go to most of GitHubs, you have a section on Python that's like how to troubleshoot on M1 Mac chips, because it really has been an issue for a lot of people. So very few of you have worked with Python, so we see how it's going to go. Maybe we take a little bit more time to address that. Cool. So we're gonna go. So we're gonna import the library reticulate. So this might take a while to install. And then we really have to check that you have your reticulate environment set up. If you don't have this, the internal configuration of the RStudio and this environment, they will not be able to find your Python path. So anything that we are going to do, it basically is going to complain that you cannot find Python or you cannot find the right path. And how to do this, it's very machine specific, but it's not completely the end of the world. And even there are functions that I think my and Python. Nope. Okay, it's virtual NV create, for instance, that help you do that from the RStudio, from R itself. So it should help you create a environment. That being said, I myself, every time I use Reticulate, I have not been very successful with this here. So my tip would be to try to use the terminal. So here you just have the story where I'm at. And then there are quite a lot of solutions. The RStudio especially has this page that helps you set up your environment. And that really works for me most of the time. And also, if you never use Python, you might need help creating your virtual environment in the first place. So you can check the docs at the Python library. So to me, to get this done, and if this is empty for you now, it's okay. We can take a look at that later. For me, this was the process. So I had to go into my file. So I had to go and use the terminal. And that might look different for you because I'm on a Linux machine. And I created my Python environment and I explicitly pass it to say my reticulate Python is on this folder. And that's what works for me. So once you figure this part out, and this is kind of the not so nice part, once you figure that part out, it's pretty easy, especially when you are in a R Markdown document such as ours, because you can do Python, and then you're just saying hello world from Python. And then if you pay attention, your console turns into a Python console. And this just blows my mind. So you cannot use alt syntax here anymore. Like, this is not valid. So if you want to compare, well, B is not defined, but this is not valid anymore. Like, you cannot do that. So in Python, for instance, the assignment is always this. So we're not gonna, no, we don't want to assign A because A is already our string. But maybe we can assign B to say our first variable Python from R. And then it's going to be there. So I think that's pretty cool that you can just have a Python terminal from R. Mind-blowing. And if you want to go back to your original terminal, you can just exit. And then you're going to be again on, so maybe not B, so you're going to be again on your R console, and you can check here up top that you are indeed there. And this is R again. It's pretty, it just blows my mind every time I do this.
Sorry, how do I get to the Python terminal again?
How can you?
Go to
really
the
have
Python.
I
how
really
do I
want with your mic. Like, can you speak closer to your mic? Because it's always like cutting towards the end.
Okay, how do I go to the Python terminal?
Okay, so do you have, when you do this, does it appear? Do you have this set up?
Yes.
Okay, cool.
That-
So when you do this, it automatically gonna give you this interface. If you call Python, like if you're just gonna press here, it's gonna give you the interface. Is that not the case for you? If that's not working, you can also try help Python. That's also gonna open Python. Sorry, Repel Python.
Okay. I got the function now. It's that, yeah, this.
Is it working now?
Yes, I just need to know the function, which is the repel _ Python.
Okay.
How to get to the Python terminal.
Cool. Okay, that's pretty cool. Okay, so we can exit again, and then okay, we can run stuff in R, but then how do we get stuff from R to Python? Basically, you just call Py. Oops, sorry. Just call Py, and then it's gonna give you whatever thing that you put it there, and it's gonna convert to the nearest type you can find in R, basically. So we can get back our hello world from Python in R. And you can do the opposite. You can create a variable in R, and then you can call that variable in Python. So we can just carry, oops. Okay, so you have all the variables you created there here now. So you can get an array from the Euclidean matrix that you did before in our other script. If you still have but it's gonna be true if you didn't clean your environment in R. But you can basically send objects back and forth rather easily, and that's kind of where this shines. So we can start by generating our data set. So Python, the equivalent to library, basically, like when you do library in a given package. So I don't know, let's see the scheme R was using earlier.
You're in the Python terminal.
Oh, there we go. Okay. So this is library basically. In Python is this syntax. So here we are now importing NumPy, but you can import NumPy, and then you can put the function you want to import, and then S, and then you can put a name to that function you want to import. So whatever method you want in NumPy, can just do now from that. And in R, usually when you have a library, you don't need to call the methods, the libraries itself. That's not the same in Python. So you can say here that in Python, I have the library, and then I'm calling a method from the library, and from that, I am passing a vector. So this next line, instead of, for instance, I'm importing this entire module on this library as BLT. From like the next line, I'm just choosing from scikit-learn, I just want to import manifold and datasets. So I'm just importing one function. And then when I do that, when I have only one function, then yes, I can do that pretty similar. So I can do datasets, and then I'm just passing the function make a Swiss roll, which makes me the Swiss roll. And then you can see that the return, it gives you two different things. It gives you the point itself. So with your coordinates, so X, Y, and Z. But it also gives you the colors. So that's going to be very important for us later. Then we can even plot figures from Python. It's not going to plot here directly. So I'm going to show you the reticulate file. So let's stop sharing this and show you what it looks like directly on the HTML. So window, let's do Chrome tab. So there we go. They'll have a Swiss roll. And you can see that the plotting style or the plotting syntax in R is in Python is very different from R, especially matplotlib itself. And it takes me to this day, every time I plot something in Python, I just remember the functions in R. So you don't need to worry too much about this, just to show that indeed you can do this from the Markdown. So let's go back to
how did you see the plot? Did you have to knit it?
Yeah, I had to knit it.
Okay, cool. Thank you.
I'm not sure if there's a way around it in the RStudio. It's never been super an issue for me, but DITs and PDFs, that they're very, very okay. They never failed so far, at least. So the chat, if when you want. Yes, yes, Sarah, you're right. And then there's something funny going on in the M1 that we can check later. Okay. So then the syntax on the manifold, you just call the manifold and the function you want to. And then I'm just initially rendering. The perplexity, it's a factor that affects basically how your data is projected and initialized, if I'm not mistaken. So we can check those parameters. So we can actually run from R and see the helper function. And then you can have the list of parameters that you have. So in this case, it's giving me the entire manifold thing, just not super helpful because I have to find the particular class that I'm looking for. So, no, so here we go. We have a class Tisni and then the perplexity. So basically, it's just it's related to the nearest neighbors. So yeah, they really do affect how your data holds. Oh yeah, actually, this is the thing I was thinking about, the early exaggeration that really does affected how clumped or how spaced out your clusters are. And then you can do that. You might need to install the package if you have not. And then you can fit your transform. It's going to take a little bit. And then the syntax is it would be analogous to doing prep and bake, for instance, because it's not only fitting, but it's also giving you the result from the transformation. If you just fit, you would not have the result back. And you can see that fitted it's a array, it's not a method. So you can call it from Porphin R, and you can see the results for t-SNE and your t-SNE that you ran in Python from R. So it's pretty cool that you can kind of imagine how the variables in the Swiss roll are related. And we're super short on time, so I'm just going to show you this last one. So there is also a UMath function in Python, but it's really I tested this tutorial in different computers, and the only computer I could manage to run was my work computer. All the other computers, it took me at least 15 minutes to configure the environment. So that's not doable, but you can definitely do this, and the syntax is very much at least analogous to the one we saw here. But we can do the UMAP, and we can see that the results are comparable to the ones that we have with t-SNE. Instead, that this looks like it unfolded the row almost like it was one of those gummies that rolls itself and then try to open. It goes in the other direction, so it deforms a little bit instead of being here, and the t-SNE kind of distorted in a different sense. But anyway, they managed to reduce the data, and you can see that the color points that were tightly together on that row, and you see that the colors, they are still pretty much together, except that this green thing here, then it starts to show up only here, and then it's blob in the middle. But it's the same thing here, just a little bit more discontinuous. And there's a random dot, the random green plot here. But this is basically UMAP and t-SNE and reticulate. So what? Markdown and SAR, I wonder if it'd be different with Quartal. I have not tried Quartal yet for this, but it would be pretty cool if Quartal could handle that. Yes, it should look a little bit different. It also, if your state's different, it's gonna look different. If your random state is different, it's gonna look very different too. It will not look the same. So that's the tutorial. We still finished in time. Sorry that the last bit was a bit rushed, but let me change my screen. And this file, since you don't need to do anything, it's the same file that's there. There's no new file. I'm just going to put the one from section 2. So thank you so much, everybody that came. I think it would be nice if we just took the last few minutes to discuss everything, so we can see how it goes. I'll leave my email here in the chat. If you have any questions, you can email me or contact me via Twitter, or even open an issue on GitHub, and I usually answer pretty quickly. But if I don't answer in 2 days, I probably forgot to. I opened and I forgot to answer, so please email me again. Thank you so much for coming. It was very nice. I hope you took something from this session. And Sarah has a question: if you map sensitive to random seed or the t-SNE as well, assume if one is, if both of them are. Is UMAP? That's a really good question. I think it depends on how UMAP is being initialized, but UMAP should not be that sensitive to seeds, mostly because I think the first production from the UMAP is not. No, yeah. Okay, so in R, definitely the seed has a parameter in it, so it is sensitive to seeding, but it should be. I think it should be less sensitive to it because of the way it preserves global structure. It might just be faster in the calculations. I'm not completely sure about that. But I would expect the t-SNE would be much more sensitive, and much more sensitive to the early exaggeration parameter. You're welcome, everybody. I hope it was good and you could take away something from this. So if, I don't know if this is gonna keep on, but if anybody has an issue during the section that they couldn't solve it, right now you can ask me to. And again, thank you so much. Oh, you guys are so cute. Gonna react to everybody in the chat. Okay, everyone, that was it. Thank you so much. I hope for your crew it's still good morning. Have a nice morning. For you that are late in the evening, have a good evening too. Bye-bye. Okay, good.
Thank you.
Por mi parte, solo agradecer toda la documentación facilitada y el tutorial y bueno, todo lo bien problemas, ¿no? Que ha habido.
When you're ready, you're good to end your call, and it will end the session.
Okay, so I just close the call. I just leave. Okay. Yes. Thank you. Bye bye.
Thank you so much. Bye.